Modern electrical engineering relies on lumped element mathematics. These equations provide the macroscopic framework for designing everything from power grids to microprocessors. Most students are introduced to these concepts through a specific mental model: electricity as a fluid of electrons flowing through a copper pipe. Charles Proteus Steinmetz, the mathematician who helped standardize circuit theory, viewed this standard engineering model as a significant obstacle to understanding physics. Steinmetz dismissed the idea of localized charges residing on the surface of a wire as a prehistoric conception. In his view, the copper conductor is a dead core. It serves as a spatial guide rather than the vessel for the energy itself. The physical transfer of power occurs in the space surrounding the conductor, where fields interact in the void. If the engineers who developed modern power systems rejected the idea that electrons carry energy inside the wire, the physical metal itself serves a different purpose. The actual transfer of electrical energy occurs entirely in the theater of space surrounding the conductor. The physicist Oliver Heaviside mathematically formalized this reality. He modeled electrical power as a symmetric system of mutually embracing geometric fields in the ether. This diagram shows Heaviside's exact architecture. Lines of magnetic force wrap around the axis of the copper wire like a cylinder. Intersecting them are lines of dielectric force, radiating outward at a strict 90-degree angle. These two orthogonal fields do not exist independently. They are mechanically geared together through time, operating as a single, unified mechanism. To prove this spatial transfer is a physical reality, we have to look at classical circuit math. By applying the calculus chain rule to standard circuit equations, we can map macroscopic variables directly onto Heaviside's field geometry. A temporal derivative, the rate of change over time, is a one-dimensional calculation. It cannot describe how two fields interlock at right angles across 3 dimensions of space. Oliver Heaviside sought a mathematical language that could account for this spatial geometry. Heaviside and Josiah Willard Gibbs developed the vector analysis tools used to map these 3D interactions. They formalized the curl operator, which calculates spatial rotation. The curl matrix identifies rotational shear across the x, y, and z axes at any given point. In Faraday's and Ampere's laws, the curl dictates that a changing field acts as a rotational axis for its perpendicular counterpart. The math requires that a change in one field over time generates a 90-degree spatial rotation in the other. A change in the state of one curl requires a reaction from the other through this geometric linkage. Michael Faraday conceptualized these lines of force as the primary physical units of the electromagnetic field. Energy is stored as tension within these lines, distributed through the geometry of the surrounding space. Defining power requires tracking the expansion and contraction of these lines over time. Standard equations for magnetic and dielectric energy provide the starting point. We have magnetic energy as a function of inductance and dielectric energy as a function of capacity. Finding instantaneous power requires the time derivative of these energy states. Applying the power rule to the squared variables generates outer derivatives of 2I and 2E, which represent the tension within the field. These are multiplied by the inner temporal derivatives, di dt and dE dt, which track the movement of those field lines. After canceling the scalar fractions, the equations resolve into the products of voltage and current. Substituting flux change for voltage and current aligns the math with Steinmetz's field metrics. Capacity current is defined here as the rate of change in dielectric flux, the speed at which Faraday lines are injected into the space outside the wire. This calculus transforms energy storage equations into a dynamic map of field expansion. The inductive voltage equation mirrors the structure of Newton's second law. Because the time derivative of velocity is mathematically defined as acceleration, the differential of current explicitly isolates carriers. We can substitute this acceleration variable directly back into Steinmetz's inductive voltage equation. This table compares our modified electrical equation directly against Newton's second law of motion. The structure is identical. Voltage equates to mechanical force. The derivative of current is physical acceleration, and inductance operates exactly like mass. Inductance represents literal electrical inertia. This assembly line diagram tracks the total stored energy of the magnetic field, driven by the equation 1/2 L times I squared. To find instantaneous electrical power, we calculate the instantaneous rate of change of this stored energy. We set up the derivative and extract the constant inductance and the fraction 1/2 away from the time variable. Current squared is a time function needing the chain rule. We differentiate the outer square, yielding 2 times current, and multiply by its time derivative. We return the constants to the main path, and the fractional half perfectly cancels the two. Grouping inductance and the current derivative together gives us Steinmetz's exact definition for self-induction voltage. We substitute that voltage back into the expression. Running static stored magnetic energy through the physical progression of time outputs the fundamental electrical power law. Power equals voltage times current. Behind the algebra is a strict physical reality. To change the current inside the magnetic curl, you are forced to slice through space and generate a changing magnetic flux. That changing magnetic flux is literally the physical tension we identify as voltage. This simulation shows how that specific magnetic tension dynamically expands and ripples through the three-dimensional space outside the copper wire. As these magnetic loops expand, they physically grip the orthogonal dielectric loops. Because the fields are geared together, any change in the state of the magnetic curl forces the dielectric curl to twist into existence in response. The chain rule serves as the mathematical tracking mechanism for this spatial gear train. By separating the static tension of the field from its motion over time, the calculus proves that power is the rate at which the magnetic curl physically grips and transfers its strain into the dielectric curl. To complete the model, we shift to the capacitor and analyze the energy stored in its dielectric field. To honor the true physical architecture of the fields, we must entirely remove the variable of localized electrostatic charge from the math. We replace charge with Steinmetz's metric, dielectric flux, the continuous Faraday lines stretching through space. We configure the energy equation using these lines and extract our constants. Running the squared flux through the chain rule over time mathematically cancels the structural constants. Reassembling the remaining terms allows us to convert the raw field structure back into measurable circuit variables, voltage pressure and capacity current. Capacity current is entirely decoupled from moving point charges. Dielectric power is simply voltage pressure reacting against the raw speed or withdrawn from empty space. This split screen places the output of the magnetic chain rule directly alongside the dielectric chain rule. They reveal a perfect unified dualism. One field's power is driven by changing magnetic lines, and the other is driven by changing dielectric lines. The current passing through the magnetic curl generates the physical voltage that grips the interlocking dielectric curl. The subsequent expansion of those dielectric lines becomes the current that grips the magnetic loop back. This powerful visualization shows the infinite, mutually embracing transfer of structural strain between the two perpendicular geometry loops. Electrical power measures the rate at which these two spatial structures exchange tension, pulling on one another through the medium of time. Heaviside and Steinmetz were correct to abandon the concept of point charges on a wire, replacing them with these vast, invisible gears. The abstract equations on the whiteboard track physical geometry, translating the movement of invisible lines of force into the measurable voltages and currents of the modern world. Circuit calculus is the exact mechanical blueprint of the ether.